think there's any point saying that this is our final talk, but it is our final talk. I'm introducing Zack Tweedy. I've got to say, and I don't know how much you say about the origin of this, but it was because of our own Dr. Lynn Kaminsky being a part of Ligo, which you will be told about, but it's a fantastic project. But the international consortium working on this field came to Sonoma State for this meeting last spring. And Zack was one of the students working with Lynn, and so was out there an assistant, kind of a gopher at this thing. But you were hearing about these amazing things going on in this field. You just wait till we hear the field. It's fantastic. And you came into my lab with all this energy, going, I want to do this, you know. And then I thought, what you want to do is really hard. So that was impossible. So I said, this is kind of like, just nudged him. Here's impossible. Here's like amazing. And let's aim for amazing, but not impossible. And I have to say, Zack did a fantastic job. You will see in this talk. What has occurred is he's built something in my lab that can continue on in research. We see this. Multiple examples today. Students working in the research we're in, or one of the things that I think is special about Sonoma State within the CSU, and remember this as you're talking about your kids' education, is that at Sonoma State, the students come up with ideas and we can actually enable their own hard work and brilliance to make amazing things. And what Zack has made in my lab is something that now we will carry forward with other people doing research. He's built something that will stand. And I think I'll leave it at that. Let's all hear about simulating LIGO with Zack Tweedy.
All right, so my apologies. My voice decided to disappear on Wednesday. I'm currently in the process of recovering. Can you guys all hear me back there just fine? Yes. Okay. Can you hear me on the camera? You got my good angle? Everything? All right. No. So thank you for the introduction, Dr. Severson. Much appreciated. My name is Zack Tweedy. I'm very proud to present my research with you all today, simulating LIGO using interferometry to study the cutting edge of physics. LIGO is the Laser Interferometer and Gravitational Wave Observatory. It is one of the largest scientific collaborations in the world, and unlike most observatories, this does not look at the sky. It makes detections that are on scale of protons, and in 2015 they made a discovery of a gravitational wave for which they were awarded the Nobel Prize in 2017. A gravitational wave is most simply a ripple in space-time. It's brought about by the collision of two supermassive black holes billions of light years away. This can most aptly be seen similar to when you roll out a carpet and you see that wave kind of travel through, except this is the universe. One of these things are, this gravitational wave, it's kind of a chirp and it's very, very small, so it's very, very difficult to detect. A little bit of history. 100 years ago, in 1916, Einstein originally prophesied this gravitational wave through his general theory of relativity, but he decided that it was too difficult for humans to detect. 50 years later, we discovered a way that we might be able to make that detection, and then 50 years after that, we finally made that detection. So LIGO uses a physics subset called interferometry to make these detections. Interferometry is using light to make measurements. You can see here this Michelson interferometer is much like what LIGO uses to make their own detections, and it's quite simple. It consists of a laser setup striking a beam splitter, which then splits this off into two mirrors. These mirrors then bounce back into this beam splitter and strike a screen. Now when everything is hunky-dory, you find an interference fringe pattern that looks like a bullseye. If those mirrors are not moving, that bullseye pattern is very stable. However, as these mirrors jiggle and shift, the interference fringe pattern will grow and expand or even jostle. It is the measurement of that movement which allows you to make measurements. Now I want to make sure that everyone's understanding here. These fringe patterns, one dark band plus one light band is equivalent to one wavelength of light. So if we were to make another comparison to a human hair is about 50 microns. The order of magnitude that we are making measurements on are about 6,000 times smaller than the width of a human hair. And that's just the basic one. LIGO is able to make a detection that is 1/10,000th the width of a proton. Completely extraordinary. So, bringing it back. LIGO, this is LIGO Hanford, has two 4-kilometer long tubes that extend all the way out here. The laser is somewhere over here, and the screen is somewhere over here. Now if I'm two black holes, black hole A, black hole B, they swirl around each other and they create distortions in space and time. And as they rotate around each other faster and faster, they eventually collide and send a chirp. Now if I'm LIGO and I'm using my mirrors, as the gravitational wave comes by, the mirrors are going to shift and they're going to get faster and faster and faster until suddenly the chirp disappears. Now LIGO Hanford can't make this detection on its own, so they have to call their buddy LIGO Livingston and let's say, hey, did you just get that? And the Livingston will say, yeah, we just got that. That's exactly what happened in 2015. You notice here that the frequency, this is time, the frequency is increasing as well as the amplitude or the strength of the shifts in the gravitational wave over time. This chirp, or this signal, is what we call a chirp. And it takes both LIGO Hanford and LIGO Livingston to make the same detection in order to make its measurement. So with all of that background info, my goal is to create a LIGO simulator. Now obviously I will not have the same scale or precision that LIGO will have. However, what I can do is build kind of a scale model of what LIGO does. I know what a gravitational wave looks like because we've already detected it, so I'm able to simulate that through sound waves. Once I insert my sound wave into my interferometer, I can then develop code and extract that signal out. So this is my interferometer. It's much like LIGO's interferometer and it's much like the interferometer we saw earlier. Here's my laser. This is a 633 nanometer helium neon class 3B laser. It's not really eye safe, so don't look at it. It's also red light and it's kind of easy to use. This is a Thor Labs beam splitter, 92% reflected or 92% transmitted, 8% reflected. That means that if I have my laser beam here and it strikes my beam splitter, 92% goes through and 8% gets reflected out. This is my test mirror. It does not move. This is my reference mirror. It does move, and you can see here I inserted a little speaker system attached to a wooden block, and that'll allow the mirror to jostle. This is my camera or my screen. This is a Firefly MV03. It has a frame rate of about 120 frames per second. A high frame rate is extraordinarily necessary in order to catch these quick movements and fringe shifts despite all this noise. Speaking of noise, there is a lot of different types of noise that I needed to account for within my system. Such noises include if the AC is on, the molecules pushing into my system will jostle the mirrors a bit and make noise in my signal. If I'm breathing too close to the signal, the mirrors will jostle. If my hands are too close to the mirrors, the thermal expansion will actually push the mirrors out. If Dr. Shi is in his office 2 doors down grading papers, I'll pick it up. If EJ is running his HVAC stuff, I'll be able to pick it up. So it's very difficult to make these very fine measurements because the mirrors are so sensitive. And that was kind of one of the biggest issues that I struggled with during this project. However, I used calibration methods in this equation here. You can precisely count the number of fringes based upon the distance you travel and the wavelength that you're using. So I 3D printed a gear system that would push my mirror a very specified amount and then counted the fringes on my video to redetermine that wavelength that I had used. Excuse me. So with this experiment in place and all these noises accounted for, I determined there is approximately 2% error in my system. So my laser has a wavelength of 633 nanometers. Well, my interferometer says 633 plus or minus 2%. It's pretty good. Once I finished calibrating my system, I was able to generate a signal and insert a sound wave into it. Right here you'll see a function generator and an oscilloscope on the other side that allow me to modulate a wave and send it through to my speaker. However, as I transitioned out of that, I realized I needed to switch between just amplitude and a frequency shift plus an amplitude. I did this by using a tuning generator I found online. It was very useful for tuning equipment or like musical instruments and that sort of thing, and it was perfect for this. I used a processing language called IDL, or Interactive Data Language. Basically, what my code does is it takes a video, it chops that video into several thousand frames, and then for each frame runs arrays of testing and data acquisition on it. At the end of my code, I'm able to extract the phase, where those fringes are, the frequency and how quick they are moving, and how far each fringe is moving over the lifetime of my movie. This is a sample video of what I was staring at for hours at a time. As you can see, the fringes are moving back and forth very slowly, but over the lifetime of the movie, the fringes actually speed up, and if you look very closely, they actually move farther and farther apart, or farther and farther to the left and right, excuse me. This is a plot of my phase, or where the fringes are actually located for each frame. Now in that previous video, that was only 12 seconds, but that's approximately 1,500 frames of data that I needed to take and analyze. You can see here, the fringes are moving back and forth very slowly, and they're not moving very far. But towards the end, they move very quickly, and they're moving very far apart. So, bringing it back. We have LIGO's gravitational wave coming from two supermassive black holes. They collide and send this chirp all throughout space. LIGO uses incredible interferometry techniques to make these measurements. I submit a gravitational wave through my own speaker, and I'm able to get the same results. Notice here the frequency and the time, but also notice how bright this thing gets over the lifetime of my movie. The brighter the data sample, the higher the amplitude. So, at the end, I have successfully completed my Ligo Simulator. But, now what, right? Well, this project serves, it's greater than me. It serves as a foundational test bed for other students. There are a variety of different ways that someone else can come in and make slight adjustments to this project without changing the core and the crux of what I'm actually doing here. As an example, you can change either the test mirror or my reference mirror with a MEMS deformable mirror. This is a mirror that changes with respect to its voltage applied. So, you can insert noise into the signal and then develop code further to extract noise out of that signal and get the same gravitational wave chirp. Furthermore, you can use different types of software in order to change the way this function or the code functions. I used IDL because it's a really good image processing software and was capable of taking a frame individually. However, a student could use Python or C++ to do the same thing that I'm doing through different methodologies. Further still, you can change the laser type that you're using. LIGO has a frequency of 1064 Hertz. This means that it has a very short wavelength, which allows very fine movements and fringes. I use a much higher wavelength laser, which allows me to have more broader fringes. A student could have an even longer wavelength laser and have even coarser fringes assigned to it. Furthermore, this could also serve as a teachable experiment in a lab. Dr. Severson was talking about how you could transition this into a laboratory setting and learn hands-on experience on Fourier transforms and the importance of using light to make measurements. Finally, this project serves as a community outreach project. For the layperson who doesn't really want to get into the weeds of what LIGO does, they can holistically look at what LIGO is and how they function and how they operate. So I want to thank Dr. Severson, my advisor, for constantly pushing me onto the next task to do. Dr. Kaminsky for giving me the brainchild for this project that I probably should have thought of instead of squeezed light. Ryan Brown for assisting me in construction and gathering thoughts and kind of what to do next. And Steve Anderson for helping me in the physical construction of the interferometer. I'd also like to thank my family for showing up here today. And I'd like to thank all of you for sitting here for the last 3 hours to listen to all of us talk.
Zach didn't say it, but those pictures are from the reception with.
Oh, yeah. So these two, this guy and this guy, those are, yeah, those are the Nobel laureates.
That's where we have to talk to.
Yeah. And
That's why we're all dressed up.
Kip Thorne is also the main science writer for Interstellar, if anybody knows about that. Yeah, so I got to shake his hand and stand next to him for a couple seconds. It was awesome. I'm happy to take any questions if you guys have them. Yeah.
Is the increase in frequency, like, is that indicative of how fast the black holes are, like, swirling around each other?
Yeah, so for the lay people, yeah, so as they get closer together, they speed up.
Yeah.
And that increases their frequency.
So I know Ligo had a lot of noise problems for a long, long time, and that's one reason it couldn't make the measurements and got rid of those. Do you know, were there solutions to the noise problems similar to your solution to the noise problems, or are they?
Well,
you have this nice analogy.
yeah, so a lot of, yeah. So
cost,
for scale, LIGO has to care about the seismic activity of the Earth in order to make its measurements. So, you know, if there's an earthquake in China, like that's it, like they're done. A lot of mine was thoughts and prayers. I spent a lot of time hoping and praying that nobody else was in the lab next to me. But I also needed to take measurements, like I needed to do everything with the lights off. I had to stay away from my interferometer when it was in operation. I couldn't really breathe on it if I was trying to do anything like that. I needed to be very, very precise in what I was doing. If I was moving, just stepping around the lab would cause interference fringe patterns to shift. So I needed to be very careful in what I was doing. I played around with the idea of using a cover, but then I realized that I wanted to see what I was doing, and I wanted to see it work. So I kind of shied away from that. But that would be a good step to take away the AC unit blowing molecules onto it. Yeah.
So Zack, you have a slide that compares LIGO's data and your data. Yeah. So here, so tell me how you actually control your function generator. Do you have? Do you use IDEAL? Do you use another language to program the?
So for the actual insertion of the function, I used a tuning generator, which I found online.
Okay.
And the tuning generator was very specific. It gave you a frequency range that you could use, and it allowed you to control how the frequency would change. So in this case, I told it to go from 1 hertz to 15 hertz, and I wanted that change to be exponential.
Is that like a voltage-driven?
I believe it simply plays a tune out of your computer. So I believe it just sends the tuning generator just sends it to your computer. Hey, play this tone or play this hertz. Okay. Yeah.
All right, let's thank Zack. That's it. I would like to say that there's some fantastic things to say. That the students have done this individually, but the families my kids are growing. I'm like thinking about them going away to college, and it's been a pleasure for us in the department to have this interaction with your students for these number of years, for hopefully 4 or 5 years, and so you are very proud of them.
And as our last official, my last official action as chair, I will pass the official chair.
Not that I ever actually used it.
I was about to say, you never used it.